faster than a speeding bullet, 6 times hotter than the surface of the sun. It seems to defy the laws of gravity and can strike you dead. Lightning. Now, we reveal dramatic new discoveries, shocking experiments that prove lightning is one of the weirdest, most destructive, and important phenomena on Earth. Lightning strikes. Giant sparks of static electricity tear through the atmosphere at 60 million miles an hour. Up to 1 billion volts rip the air apart. In that instant, the current creates light waves. We see a brilliant bolt of light race across the sky. Air inside heats up to more than 50,000 degrees Fahrenheit. It expands so rapidly, it explodes. We hear a deafening clap of thunder. It all happens in less than the blink of an eye, up to 8 million times every day. This is one of nature's most frequent, best observed phenomena. But it's also one of the least understood.
We probably know more about how a star explodes halfway across the galaxy than how lightning works just a few miles above our heads.
Scientists are using every technological tool in the box to see lightning as it's never been seen before. And they're discovering that it's more powerful.
You're talking about something that's up to 1 billion volts. It's 200,000 amps. It's a small nuclear power plant. It's huge.
And more important than ever imagined.
It's probably one of those fundamental parts of the equation that really contribute to life on Earth.
To unlock its secrets, we follow a lightning bolt on its journey from creation to destruction and beyond. Few people have experienced lightning's awesome power more closely than former stockbroker Michael Utley. May 2000. Utley is playing golf at his local course in Cape Cod, Massachusetts. Overhead, a storm gathers. 30,000 amps of electricity burns its way through the atmosphere at 60 million miles an hour and heads straight toward Utley. The warning siren sounds. It's the last thing he remembers.
The first thing that I remember after the strike was 38 days after it happened.
In less than half a second, his life changed forever.
I opened my eyes and realized I was in an ambulance. And I had a trach, so I couldn't speak, so it was kind of like The Godfather, and I was like, where am I? And he looked at me and he said, you're on your way to rehab. You were struck by lightning a month ago.
Utley never saw the bolt that hit him. He has no memory of that terrible day. We reconstruct those missing moments and step into Utley's shoes to follow a lightning bolt as it rips through the body and examine its devastating effects in forensic detail. We begin with the moment of impact. Lightning strikes. Electricity tears through your body and stops your heart dead.
The lightning goes through the body and it stops the heart. And you're 100% dependent on somebody around you to do CPR at that point. So you're just laying there, you're not breathing, your heart stopped, and that's it.
Resuscitation brings you back to life, but your heart rate is still erratic. The race is on to reach the ER. The emergency department at the University of Illinois in Chicago. Get struck by lightning in the Windy City, and this could be the first place you'll come. And the first person you'll see will probably be Dr. Mary Ann Cooper, emergency MD, and head of the Lightning Injury Research Program.
The #1 cause of death from lightning is cardiac arrest at the time of the injury.
The current hitches a lift on the body's own electrical highway. Route 1, the autonomic nervous system. It runs down your spine and controls involuntary functions, breathing, digestion, heartbeat. Roots 2 and 3, blood and muscle, full of electrolytes, acids, salts, and other chemicals, essential for life, and electrically conductive. Together they offer the current a route through the body, straight to your heart. The heart's internal pacemaker generates electrical currents that control its rhythm. Hit this with a high voltage current, and the rhythm is disrupted, or worse. But even if you survive the shock, a series of bizarre and traumatic injuries could still assault your body. A strike can cause blood vessels to spasm and leave you temporarily paralyzed.
When you look at the extremities, they're cold, mottled, blue. Look for all of the world like they're dead.
I was pretty much paralyzed, and I couldn't swallow, I couldn't talk. My body was completely fried.
For Utley, nerve and muscle damage means years of grueling rehab. But some injuries last a lifetime. A strike near the head sends current into the eyes and can detach the retina. The shock wave can rupture the eardrums and can sometimes fracture the skull. Lightning flowers, known as Lichtenberg marks. The current ruptures tiny capillaries to create a fossilized record of its journey across the skin. The same process can sometimes be seen on a golf course, but not all the effects of lightning are as easy to see.
I am definitely not the same person that my wife married prior to the incident. I've changed.
Before the strike, Utley was a ski instructor, an extreme sports enthusiast.
I used to have an edge. I used to be very, very good. Now, I'm still pretty good if I find all the notes. I kind of kid. It's frustrating. It's without a doubt. You live life on a much different level.
Lightning's deadly trail of destruction, from the nerves to the heart. Nothing is safe. But despite all this, 90% of strike victims survive. Survivor Michael Utley wants to know why. To find out, Utley will witness a dramatic demonstration at Lightning Technologies in Pittsfield, Massachusetts.
What we're doing here is trying to see how the lightning might flash across the surface of a human being.
Chief Engineer Andy Plummer is in charge of testing and devising lightning protection systems. His plan, to hit this mannequin with 1 megavolt of electricity and recreate the split seconds that changed Michael's life forever.
I would imagine that it wouldn't take much of the current to stop the heart.
I think it doesn't take very much at all.
So even if 90% of it goes outside, the little bit that goes through does enough.
They recreate conditions on the golf course. Utley was holding a putter. Metal conducts electricity. It was a hot day. He was sweating. This too is conductive. Could these two factors explain his survival?
Human sweat has a little bit of conductivity, so Bob here is putting just some salt solution just to simulate the conductivity that existed on you the day you were struck by lightning.
Excellent.
Okay, Bob, start charging. 5, 4, 3, 2, 1.
The strike is so fast that we need to freeze the moment of impact. Sweat conducts the huge bolt of electricity down the body's right side. The metal putter provides a path to the ground. The lethal current is diverted away from the major organs.
We can see on the mannequin here.
The experiment suggests that for most strike survivors, there are other factors at play, such as the putter or the sweat, diverting the deadly current and explaining their survival. It seems Utley may owe his life to these two simple things. It's a life he's still battling to rebuild. Today he enjoys a regular game of golf and uses the very same putter that saved his life. But he takes no chances.
If there was one thing that I could tell people about lightning, it would be when thunder roars, go indoors. There's no place safe outside in a thunderstorm.
We've seen lightning's deadly force. Now, we need to know what it is. What creates this awesome power? That quest takes us to one of the world's stormiest places and some of the most spectacular lightning on Earth.
Naked Science is presented by Acura.
We're following a lightning bolt on its journey through the atmosphere. We've seen what happens when a storm unleashes its awesome power. Now, let's rewind to the moments before lightning strikes to investigate what triggers this mysterious phenomenon. Our journey takes us to a city that's home to some of the world's most violent lightning storms. Darwin, Northern Australia. In just a few hours, it can take as many as 1,600 strikes. Darwin is the perfect place to investigate one of nature's biggest mysteries. What sparks a lightning bolt? An international team of scientists are here to find out. They use radar and a fleet of aircraft to look for the answer deep inside Darwin's monster storm clouds. A potent cocktail of heat and moist tropical air means these are no ordinary clouds. Called cumulonimbus, they can rise up to 40,000 feet at speeds of 60 miles an hour. 13 miles up, twice as high as a passenger jet. Above the storm, a modified former Russian spy plane collects data about the cloud below. Somewhere inside this cloud, lightning is preparing to strike. Understanding how has puzzled scientists for centuries. But they think the cloud acts as a giant electrical generator. Inside the cloud, tiny water droplets rise upward. They freeze and fall back down as ice. They rub against each other. Electrically charged particles transfer from one to the other. The water and ice particles that were previously neutral are now either positively or negatively charged. The negative particles sink to the bottom of the cloud. The positive rise to the top, separating the positive and negative charges. When they reunite, lightning will strike. That's the theory, but the reality is even stranger. Air is not a good conductor. Electricity can't pass through it easily. To let the current through, the air's atomic structure must literally break apart. To do that takes millions, even billions of volts. Scientists search the skies for this huge electrical charge. But even in Darwin's massive storm clouds, it's never been found. In the story of lightning, there's a piece missing. It's a puzzle that fascinates physicist Joe Dwyer from Florida Institute of Technology.
With lightning, it's almost embarrassing. We've been studying lightning since the time of Franklin, and for over 200 years, we still haven't answered the big questions. How does lightning work? How does it get started up in the thunderstorms? How does it propagate for miles through the air from way up there where it's initiated down to our feet?
One thing we can be sure of, lightning is static electricity, and you can make it at home.
Let me take my shoes off, and when I do, I'm going to rub my feet on the carpet. As I rub my feet, friction is going to separate electrical charge. Positive charge is going one way, negative charge the other. Now when charges separate, they want to get back together. A large electric field can build up, and when this happens, you can get a spark. We think that something like that is going on inside a thundercloud when it makes lightning.
To send a current across this tiny distance takes up to 25,000 volts. But lightning bolts can be up to 120 miles long. Sending a current through this much air takes millions of volts. A massive electrical charge that so far scientists have failed to find.
You have to ask, well, where is the finger that's concentrating the charge to making the big fields to produce the spark? And we're having a really hard time figuring out what that finger is.
Thunderstorms are violent. Lightning is unpredictable. Getting close enough to make measurements is virtually impossible. Scientists can't get to the lightning, so at the University of Florida's International Center for Lightning Research, they bring the lightning to the scientists.
What we did is that we used rocket-triggered lightning. You can tell lightning where and when to strike.
Dwyer and the team fire a rocket into a charged storm cloud.
Ready to fire. Arming rocket. 5, 4, 3, 2, 1, fire.
It trails a copper wire that acts like a lightning conductor. Millions of volts of electricity race from the cloud to the ground. Dwyer uses data from this to investigate how lightning can pass through miles of air. And he looks for the answer in outer space. In a galaxy far away, a star explodes. Millions of microscopic electrically charged particles are forced out into space. These are cosmic rays. Traveling at nearly the speed of light, they race across millions of miles, millions of light years to reach Earth. Dwyer wonders, could cosmic rays explain how electricity travels through miles of air? Billions of these rays bombard our planet every second. They're invisible and inaudible. But when a cosmic ray travels through the atmosphere, it momentarily rips apart the air's molecular structure. This produces X-rays, electromagnetic waves of radiation, which can be measured. Could cosmic rays be the missing link in the story of a lightning bolt? It sounds like science fiction. Even the optimistic Dwyer thinks it's a long shot.
When we got our first triggered lightning and made our first X-ray measurements, I didn't even get around to looking at the data for a couple weeks, because I wasn't really expecting to see anything. When I sat down finally, there on the screen was an X-ray pulse right when the lightning occurred. I thought, well, what's the chance of that happening? I mean, right there at the same time. So we looked at the next stroke, and there was another pulse, even bigger. We looked at the next stroke, another pulse, and another pulse with the next stroke. Every time we looked, we saw a big burst of X-rays hitting our instrument at the exact time that lightning struck.
To Dwyer, it's a clue. Something has changed the air's atomic structure, and he thinks that something could be cosmic rays.
For centuries, we've been laboring under the assumption that lightning is just a normal kind of discharge, like the finger touching the doorknob. We suddenly see now that this was wrong.
If Dwyer's right, when a cosmic ray hits a cloud, it causes a huge momentary surge in electricity, enough to create a spark, but too brief to be measured. The ray hurtles on toward the ground. The super-fast-moving particles collide with air molecules and rip them apart. For a fraction of a second, the air becomes electrically conductive and provides a path down which the current can run. Now, lightning can strike. A channel of negative electrical charge shoots from the bottom of a cloud. It heads toward the ground in rapid steps. Each takes just 50 millionths of a second. As it gets closer, it has a strange effect on the ground below. Positive particles in the ground, or in objects on it, are drawn up toward their negative counterparts. A storm cloud can create dozens of these negative and positive channels. Most don't connect. But when they do, millions of volts of electricity race between the cloud and the ground. Lightning travels up as well as down. The air lights up. We see lightning strike, hear the air explode. In the following thousandths of a second, any remaining charge in the cloud surges up and down the channel. The bolt may appear to flicker. Lightning really does strike more than once. And all this happens up to 8 million times every day, 100 times a second. Lightning is one of nature's most common phenomena. And if Joe Dwyer's theories are right, it's also one of the most incredible.
If these ideas are correct, then there may be a connection between the lightning that we see and a star exploding halfway across the galaxy in 1 million years ago.
In less than half a second, we've traveled from strike to spark, impact to creation, as we follow a lightning bolt. Now, in the moments after impact, we enter a bizarre world of fireballs, UFOs, and ghostly apparitions. We're following a lightning bolt on its journey through the atmosphere. We've traced its origins, investigated the terrible moment of impact. Now, our quest takes us to the moments after lightning strikes, to a twilight world that seems to come straight from the pages of a science fiction comic. March 19th, 1963. Eastern Airlines Flight EA-539 from New York to Washington. 5 minutes past midnight, the plane encounters a storm. There's a loud bang and a bright flash. Seconds later, a glowing ball emerges from the pilot's cabin. The blue-white ball hovers above the aisle and floats slowly toward the rear of the plane. It reaches the back of the plane and vanishes. Remarkably, the plane continues unharmed. But this wasn't fantasy. This was fact, and it wasn't the first account of its kind. In World War II, pilots reported strange balls of light that seemed to follow their planes. U.S. pilots named them Foo Fighters. For thousands of years, people have claimed to encounter fiery spheres as ghosts, messages from the gods, or UFOs. But there was something different about the Eastern Airlines account. The eyewitness wasn't an adrenaline-fueled fighter pilot or a medieval mystic. He was a scientist, a professor at a prestigious British university. Suddenly, scientists sat up and took notice. One scientist who's been inspired by his own close encounter is nuclear physicist Dr. Graham Hubler.
I have seen ball lightning myself, so I know that it exists.
A teenage Hubler is on a date in a park in upstate New York. A storm breaks out. The couple takes shelter in a bandstand.
And suddenly, off to our left, we're sitting there with open sides on the left and the front. Off to the left, we saw this ball approaching, ball of light. And, of course, we were terrified. What the heck was this? We didn't know what it was.
Slowly, the ball approaches.
It was about 30 yards away and coming slowly at us, just kind of drifting along. And we're looking at this thing and we were both just paralyzed, actually.
To their horror, it enters the bandstand and rolls across the floor, past the couple's feet with a strange sound.
The sound it was making was like a freshly struck match.
At the other side of the bandstand, the ball leaps back up and travels out of the open side.
And it jumped right back up to about 6 feet off the ground and went out another 20, 30 feet out into the night, and then very quickly dropped to the ground and extinguished without a noise.
The experience leaves Hubler with a lifelong fascination with ball lightning. He collects thousands of eyewitness accounts. There's multiple ball lightning, balls that fell from the sky, that exploded, hissed, spun, hovered, jumped. It's even been seen to pass through solid objects without leaving a trace.
There is no good theory that exists that explains the features of ball lightning. Different theories can explain one or two of the features of ball lightning, but none really do a very good job of explaining it all.
One man who's examined all the evidence, investigated all the theories, is physicist Mark Stenhoff.
There are probably almost as many theories of ball lightning as there have been scientists investigating it.
But there is one thing almost everyone agrees on. ball lightning is probably plasma. Plasma is the commonest form of matter in the universe. The sun, fire, lightning, and the space between the stars are all plasma. It's not hard to make plasma. Run a current through a gas, and it will spontaneously emit light. But explaining how a fiery ball can materialize out of thin air has confounded scientists for centuries.
I think as soon as we see something we can't explain, particularly something as bizarre as that, we have a tendency to move outside our normal frames of reference and explain things using, if you like, rather supernatural kinds of explanations.
One of the more sensible theories is that ball lightning is produced by a rare phenomenon known as bead lightning. This footage shows a lightning bolt that appears to break into small beads. Some scientists argue that ball lightning is a plasma bead that's become separated from the bolt. But there's one big problem. Eyewitnesses talk of balls lasting minutes. These beads vanish in less than half a second.
We don't know of a way in which we could create a plasma in the atmosphere that's self-contained, that would survive for many seconds. A plasma would provide plenty of energy, but it wouldn't be able to survive for that period of time.
So if ball lightning isn't part of a lightning bolt, could it be the product of one? This strange-looking stone is the fossilized remnant of a lightning strike. Lightning strikes sandy soil. Heat and current spread through the ground. Everything in its path fuses into a solid tube. This is nature's own glass. It's called a fulgurite and can stretch to depths of 15 feet. When the tube is formed, dust is pushed up into the atmosphere. This detonation replicates the effect. Could something as simple as dust hold the key to this centuries-old mystery? Laboratory experiments prove a tiny dust ball holds its shape and ignites in an area of electrical charge. It could explain Hubler's account, but not the Eastern Airlines one.
It's extremely difficult to imagine how any chemical process could actually, if you like, invade the space inside the aircraft.
For now, ball lightning remains a mystery. But if science can unlock its secrets, ball lightning could turn out to be more than just a curiosity. It's even possible it could hold the key to a completely new source of energy.
Evidently it contains energy. Just the sheer process of glowing is sufficient to require some energy.
And if we could harness that energy, who knows what the future might hold?
Ball lightning surely exists. So it's either known physics that we have to put together in ways we haven't thought of before, or it's a totally new physical phenomenon, which is very exciting, that will lead us into some new technology or new physics.
The mystery of ball lightning is yet to be solved, and it's not the only strange phenomenon to occur in the moments after lightning strikes. Look above the clouds, and the story gets even stranger.
Look! What was there? Oh yeah! You see it? Yes!
On our journey following a lightning bolt, we ventured beyond the frontiers of science. But this is just the beginning. Seconds after lightning strikes, high above a thundercloud, a strange new phenomenon appears. July 6, 1989. Physicists from the University of Minnesota test out a new low-light camera. They plan to use it for a high-altitude rocket experiment. They point the camera east, a random choice, at some stars and what looks like a distant thunderstorm. They play the tape back. Something catches their attention. Two funnel-shaped flashes of light. They last for just a few thousandths of a second. The team estimates that the flashes are 20 miles above the clouds and an astonishing 12 miles tall. By pure chance, they've captured something new to science. From his research lab at Duke University, North Carolina, Professor Steve Kummer searches for these strange specters.
It's exciting to be part of something fundamentally new that no one else has seen before, and it's kind of a big surprise that these things have been there the whole time and nobody knew about it.
The twin pillars of lights flicker above a thunderstorm in the distance. So, what are they? Around the world, lightning scientists are on the hunt to find out. They don't have to look far. Scientists review hundreds of hours of video taken from the space shuttle. To their amazement, there are dozens of these strange apparitions, just waiting to be identified. Low-light cameras are trained on the skies. High-altitude aircraft fly above storms. Soon, there are thousands of recorded sightings.
Everybody was surprised by how common they in fact were. It's just one of those cases, once you know what you're looking for, all of a sudden you see a lot of them.
Scientists call them sprites because of their elusive, ghostly appearance. They seem to dance above the thunderclouds in the night sky. In groups of 2 or 3, they last less than 10,000ths of a second. Researchers from the University of Alaska Fairbanks calculate they occur in the middle atmosphere, 25 to 60 miles above the Earth, and can extend up to 30 miles across. Observations suggest sprites are related to lightning. But how? In a field in North Carolina, antennae pick up the radio signals produced by lightning. Steve Kummer uses these to listen to the radio noise made by individual lightning bolts. The equipment is so sensitive, he can detect lightning as it happens anywhere on Earth.
Every one of these individual pulses is one of those radio pulses from a lightning stroke somewhere in the globe.
Kummer uses this data to measure the size of each bolt. He matches this with sightings of sprites from other research stations. A pattern emerges. Sprites occur in the fractions of a second after lightning strikes, but only after the most powerful lightning bolts. Kummer thinks this huge release of energy causes a disturbance in the atmosphere above. This high-speed footage, the most detailed film of a sprite ever shot, supports Kummer's theory. 45 miles up, electrical charge momentarily increases. It triggers a giant spark. Millions of electrically charged particles accelerate outward at 33 million feet per second.
Sprites tend to be about 40 miles high. The bottom here is maybe 25 miles, and the top is 60 or 65 miles.
Sprites come in many shapes and sizes, from the so-called A-bomb sprite, up to 60 miles in diameter, to a tall, skinny one, less than a mile wide, and nicknamed the Diet Sprite. 5 years after the first sprite was spotted, researchers from the University of Alaska Fairbanks hunt for sprites high above a monster storm. They use a sensitive low-light camera and capture the first ever color images of sprites. It's a spectacular surprise. What causes this colorful display? With each new discovery come new questions. But sprites are elusive, unpredictable, and almost impossible to observe at close range. So Earl Williams from MIT made his own. He calls it Sprite in a Bottle. In a disused printing factory in Brockton, Massachusetts, Williams and his team use a plexiglass tube, an old steering wheel, and plenty of ingenuity to create their very own Sprite. They recreate conditions in the middle atmosphere, 50 miles above the Earth.
There's the good Sprite light. We start with a tube filled with air at atmospheric pressure, like the air in this room we're breathing. With vacuum pumps beneath the table, we pump the tube down to pressures corresponding to 50-mile altitude.
By running an electrical current through the tube, they create a magical light show. It's the same process that lights up Las Vegas. The neon gas in these tubes is invisible, but run a current through it, and it produces colored light. In the atmosphere, most of the gas is nitrogen. Hit the air near the ground with a current, and it produces a dazzling white light. But change the pressure, and the color changes too. 50 miles up in the Earth's atmosphere, low pressure means nitrogen produces red light. But as the Sprite stretches toward Earth, air pressure increases under gravity. The color changes to purple and then blue. In the skies, Sprites last less than 10,000ths of a second. But with the Sprite in the bottle, Williams can study the forces that shape them in his own time. But even in the controlled conditions of the lab, the Sprite is a volatile creature.
Okay, here I'm going to let in air.
Yeah, give me all you've got. Oh, that's a nice display.
Oh, that's neat.
I like that.
Nice flat discs. The Sprites are very much alive, and as you can see, the patterns in the tube are very much alive, moving and writhing around and very unsteady. Oh, that's nice. Look at that.
The bottle lets Williams look deep inside the hidden world of Sprites.
I've never seen that one before.
And discover there may be even stranger phenomena waiting to be found. Sprite scientists expect the unexpected.
What was there?
But even they aren't prepared for this.
Oh, yeah! You see it? It was so beautiful.
Puerto Rico, 2001. A jet of blue light shoots from the top of a thundercloud and travels over 40 miles into the sky. Other sightings confirm this is not a Sprite. It travels up, not down, from the cloud, not the middle atmosphere. It's an entirely new species, called a blue jet.
When I saw the videos, I was like, huh, that's pretty spectacular. Wonder what those are. Blue jets are a mystery that nobody really knows what it takes to generate them.
And it doesn't stop there. Next come an even rarer species, elves. A pulse from a lightning bolt triggers a horizontal halo of light about 60 miles above the Earth that spreads out rapidly to a diameter of up to 250 miles.
Just about everybody who has gone with a new instrument or to a new region of the world to look above thunderstorms for something new, they have found something new.
Lightning's weird offspring inhabit a world that we've only glimpsed. Too high for balloon or aircraft samples, too low for satellites. Like the depths of the oceans, nobody knows what other creatures wait to be discovered.
Since there have been so many things discovered in the last 15 years, new things, it would not surprise me at all if there were more things out there waiting to be discovered.
We followed a lightning bolt on its way through the Earth's atmosphere, from its devastating impact on the ground to its spectacular after effects above the clouds. Now our journey takes us into outer space as we discover why life as we know it could depend on lightning. We followed lightning from creation to destruction and beyond. Now we travel into space for the final stage of lightning's strange journey. The Cold War, a top-secret U.S. operation, codename Starfish Prime. The objective, to investigate the effects of a nuclear war in space. July 9th, 1962. A 1.5 megaton nuclear warhead is detonated 250 miles above the Pacific Ocean. The explosion takes place in an area of natural radiation called the Van Allen belts. Wrapped around the Earth like two giant donuts, they're full of deadly radioactive particles and a threat to astronauts and satellites. At NASA Goddard Space Flight Center near Washington, D.C., Jim Green monitors the radiation in the belts.
It's a very hazardous area because
These particles are moving so fast they'll move through skin, through flesh, tissues, also through spacecraft, damaging delicate circuits and eventually leading to satellites that will no longer function in space.
Between the belts is an area with much less radiation, called the safe slot. It's home to commercial satellites, operating in the safety of its low radiation environment. But the Starfish Prime warhead sends a massive dose of radiation straight into the safe slot. Radiation levels soar. Satellites cease to function. But then, just a few weeks later, the slot is free of radiation. NASA scientists are stunned. Something has recreated the safe slot. What?
We have been on the hunt to determine why that slot region is there ever since.
Soon there's a breakthrough. Researchers realize violent solar storms pump radioactive particles into space. When these head in our direction, radiation saturates the safe slot. Then, as if by magic, it clears, and the slot becomes safe again. But not all at once. And that's the vital clue. Whatever clears the safe slot seems to be more effective at some times than others.
It's more intense on the day side than it is on the night side, and it's more intense during the summer than it is in the winter.
The evidence points to the sun. But in 2004, Green takes a chance look at a magazine, and everything changes. An article on the distribution of lightning captures his attention.
The beautiful maps of lightning changed my concept of where lightning was actually being generated, drew my attention to the article immediately.
Green notices lightning exhibits exactly the same characteristics as the clearance of the safe slot. It occurs more over land than sea, more during the day than night, more in the summer than the winter. It's a match.
That was the time that we then knew that this had to be related to phenomena that was occurring on the Earth. And the only thing, of course, that we know enters into space is lightning.
But how could lightning on Earth affect the safe slot 4,000 miles up? A lightning bolt tears through the air. It doesn't just produce light and sound. It also creates radio waves. Turn on your radio when there's a storm nearby, and you can hear them as interference. But tune in with an all-frequencies receiver, and you can pick up more than just crackle. This eerie whistling is the sound of those radio waves after they've traveled through space.
What we've been listening to are lightning spherics, and these are emissions that occur from lightning hundreds of miles away that are propagated to us and are received in our antennas.
Green realizes that these radio waves are the missing link. They connect lightning on Earth with the safe slot in space.
We never realized the importance that the ground is having on space.
In 2005, Jim and his team come up with a radical new theory. Less than a second after a lightning strike on Earth, the radio wave reaches the radiation belts. There it interacts with the electrically charged particles, the radiation. It forces the particles out of the safe slot. The radiation is cleared, and the safe slot returns to normal.
We always had thought about lightning in the past, I believe, as a destructive mechanism. But I think we're discovering many of its beneficial factors.
If Green is right, without lightning, radiation would soon fill the safe slot. Satellites would go down, taking out many things we've come to rely on. Global communications, navigation systems, cell phones, satellite television, all could shut down. Life as we know it would grind to a halt.
If lightning stopped tomorrow, we would see a dramatic change in the way we live today. It's probably one of those fundamental parts of the equation that really contribute to life on Earth.
Lightning. For millions of years, it stalked our darkest visions, struck terror through our oldest myths. Now we're closer than ever to unlocking its secrets. And the more we discover, the more lightning defies expectation. Its origins may lie far beyond our world. It can take strange forms and create dazzling light shows. Lightning is devastating, beautiful, and essential to life as we know it. The incredible journey of a lightning bolt, from outer space to the inner workings of the human body. Life and death, destruction and creation, all in less than the blink of an eye.